emphasize it. You know, I said that these guys for m greater than or equal to 1 are independent and identically distributed. The first guy is different, but it's going to be divided by n. It disappears anyway. You know, and now I'm summing from 1 to n minus 1. It looks like I'm not summing enough terms, but I can divide by n minus 1 instead of n. And what do I get, everybody? Don't you remember? Yeah, you said it? Yeah, the law of large numbers for independent, identically distributed random variables. Okay, so I expect you to know that this thing here converges to its mean because it's an independent and identically distributed. Now that's kind of screwed up. It's not what we want, right? I mean, what we want is gone now, but, and what is that? That mean there is actually remember, any of these BGs is just a summation of our block, you know. So I can just say, well, let's start at state x bullet and sum up to one step before I return. You know, that's the sum of our block. All right. So what's messed up here is that I stuck in a random time here. I should be divided by the same time. So I haven't got anything I want. I've got a result, but that's it. What am I going to do? Hopeless, right? Here's a fun thing. So this, of course, if this is meaningful, you know, if I say the law of large numbers, you have to have this be meaningful, right? So, for example, if G is bounded, no problem. All right. So, of course, you need conditions for this to be finite, or or well-defined. But let's assume G is, and that's right. It's a random sum. So even G bounded is a problem, right? It may be that, this doesn't make any sense even with G bounded, right? Because this might take so long to return. So we're going to need conditions for that to be true. Our Lyapunov functions will come to the rescue. So we'll get those bounds. So we need this to be, assume it's bounded. All right, so here's what's sort of fun is that I can stick in any G I want. I hate to erase this, but you've got this in your notes. So let's say, what's a fun value of G we can stick in? How about this? Try G is identically equal to 1. All right? Let's play around. We'll play around with other functions in a minute. If G is identically equal to 1, we're summing 1 up to this time t bullet. So it's just itself. Again, this was true for any function G, so long as this makes sense. All right? And so if I take G equals 1, this was a sum of G of xn. Well, G is just 1. So this sum is nothing but that. Those are the same thing. All right? And then this is just equal to that. But G is 1. So what is this sum if G is identically 1? It's just the mean return time. Now we're getting somewhere, right? So we get the expected return time. And then we can do something fun. Here's the thing is that, remember I said I don't want to divide by n, I want to divide by tau n. We know the ratio. So the limit as n goes to infinity of 1 over tau n bullet SG of tau n bullet I should have made that clear. Think of this as a little aside. All right. Now going back to NEG, this is a nice purple. This is what I care about, right? And what I can do is I can, well, no, forget it. I won't put all that space in there. Okay, so I'm just going to do a slip in an n and a 1 over n. And that thing we got here. And that thing we got here, but flipped around. So that converges to 1 over that. And that converges to that. And if you don't find that beautiful, just go and see. I have some suggestions for a psychiatrist or a depression counselor. So the law of large numbers, with these random times, unfortunately, exists, and we get this beautiful limit where we look at a regeneration cycle. The time between visits to this, it's an arbitrary state. We just picked it out, and we look at the G is a cost function. The expected cost over a cycle divided by the expected length of a cycle. All right, that's one way of representing pi of g, and this we will find that's pi of g. Fact. How about that? Fact. That's one. Remember, this section of the course is called representations. That's one representation. All right. Is that clear? What's not clear? Come on. Give me a question. The only thing that is not complete is the fact that the law of large numbers holds for ID sequences. But once you do that, you just fool around. Now, this is not the way you usually find this in books, I mean, not always. Kill all this. Can anybody think of a fun G we could plug in to get a different result? See, I don't like this ratio. That's kind of weird. What's that?
I feel like it's kind of like chain rule or something.
Oh yeah, well there is some funky chain rule going on, yeah. But there's a more standard way of writing this down, and you get it by trying another G. Now what G would make the right hand side really simple? one of no, X is rather the countable state space. So the state space might be A, B, C, D, E, F, G, H, I, J, K. No, like remember we're summing.
An indicator function.
Yeah. So suppose we made this 0, but not identically 0. Remember we're summing over a block, and we're starting at X bullet, and we're summing until just the time step before we return to X bullet. We can make this deterministic with an indicator function. So there's two notations of the same thing. You'll write indicator function of a set at X, or indicator function at X equals X bullet is, again, just a logic function. It's 1 if X equals X bullet, and it's 0 elsewhere. And so clearly, this sum is 1. So on the right-hand side here, we get to start off at X bullet, even though we didn't initially. And so here we're summing, and every term is 0 except for the first term. And so, but the I said this is pi of G. Well, what's pi of this guy here? That's this pi of X dot. Remember, this is just a dot product, and the G here is 0 everywhere except for when X equals X bullet, and then it's 1. So these are the same thing, and then I say this is 1 for the special case of G, and this is not changed. And so you put that together with this, and you get what's called Kack's theorem, which I mentioned last time. So you replace that weird thing at the bottom here by sticking a pi of X bullet here. The same thing. So that's Kack's theorem. And so then you get this really nice result. Here, I'll write down theorem for this X bullet irreducible Markov chain. So we have, if we have this, if we're an X bullet irreducible Markov chain communicating class X bullet, I could have derived all of this for any state in this communicating class. They all play the role of X bullet. They're all reachable from any initial condition, provided this is finite for one X bullet. Then we get pi. There we go. So there it is. So that's the fundamental stability criterion we need. We need really just one state for which the mean return time is finite, and then we know that an invariant probability mass function exists, and it's given by the reciprocal of the mean return time, just right there. There's the proof. It really is. And then this, of course, then we know that we need this to be finite valued, and again, Lyapunov theory does that. So to not this week, but next week. Turns out this is equivalent to what's called Forster's criterion, which is one of these Poisson inequalities. And assume finite is equivalent to this Poisson inequality. So to get this as a very, very, very weak version of this Poisson inequality we've talked about, and to get this, we need to tailor our inequality with the function g. So we'll talk about that next week. All right. Cool. Whoa. All right. So until next time. So I will amend my notes for those of you who want more, but you don't need more. This is all I want you to absorb. I don't think I'm going to prove hardly anything else. I'm going to state the CLT for you and give you an idea of why it's true. And definitely they'll get into these things, because we need this. Criterion for these guys to be finite. We'll need it for everything that follows. So again, those lecture notes, 2 representations, I don't suggest you go and read every bit of it, unless you want to do really serious research in the area. You don't need it for the course. It's just for your reference. On to office hours. Okay.